Hi everyone, so this is the first of two or possibly two review sessions, and some of you have sent me questions and I will be going over them today. So the first, actually only one person sent me questions, but it was a bunch of questions, so I'm going to do all of them. So the first question is, how can we show a language L is not recognizable? So we have a couple different ways of showing that a language is not decidable, which is mainly a reduction, not a reduction, sorry, by contradiction. So for example, we showed that ATM, if ATM is decidable, then, which is a contradiction, what we can do is to use a supposed decider for, say, ETM, and if it were decidable, then that would imply that ATM itself is decidable. But this is not the case, and so therefore ETM is undecidable. So one result that we used in multiple times is L is decidable if and only if L is recognizable and L bar is recognizable. So if we happen to show that, if we show that L is undecidable and one of two things, and let's just say that L is L is undecidable, L is recognizable, then that would imply L bar is not recognizable, because if it were, that would imply that L is decidable by the result we did before, and we know that it's not. So if it is recognizable and undecidable, then the complement is not recognizable. And similarly, if L bar is recognizable, then that would imply that L itself is not recognizable, because it's just the complement of each other. Okay, so so this is the main tool that we have used to show a language is not recognizable. So another way that we can do it is to do something similar to this part right here. So I'm not going to actually expect you to know how to do this, but it turns out that you can use a very similar idea, that if you suppose that, for example, ETM is recognizable, then, and if you can show something like this, then that would imply that ATM is not recognizable. That would imply that ATM is recognizable, sorry. So let's see. So how can we actually do this? So I'll show you one result. So we've talked about EQTM, and we've shown that it's not decidable before. And the reason was that we can use a we can suppose it were decidable, then we can get a supposed decider for ETM, but we know it's undecidable. So we can use a similar technique here. So we showed that ETM is undecidable, and so that would imply that either ETM is not recognizable, or its complement is not recognizable, or both. But we showed, in one form or another, I'm not exactly sure, but I can outline it here again, that ETM bar is recognizable. And the reason for this is to test test the first I strings for I steps. And if any of them are ever accepted, then that means that that the language of the machine is not empty, so therefore we should accept here. So ETM bar is recognizable. So that would imply here that ETM itself is not recognizable. So then suppose that EQTM were recognizable. Then that would imply that using the same technique that we did before, by making a Turing machine with empty language and then running the test of whether it's equal or not, then that would give us an answer for ETM, at least for a recognizer. So that would imply that ETM is recognizable, but this is a contradiction. So that implies that EQTM is not recognizable. So the thing is to realize about how we were able to show ETM not decidable is exactly the same idea as for showing that it's not recognizable. But you have to show first that that one of them is not recognizable. So the fact that ETM bar is recognizable, that's the only way we can show that ETM itself is not recognizable directly. So there are some languages that are not recognizable and its complement is not recognizable either. So I'll let you think about how would we actually show a language is not recognizable, nor is its complement recognizable. But the main technique, based on the question, is to use something like this. So if you happen to know that a certain language is not recognizable, and then if you can show that you have some language here that you want to show not recognizable, then can use a hypothetical recognizer for it, then if that implies that the original language is recognizable, then that would be a contradiction. So then that would imply that the one you're interested in is not recognizable. So then the second question here is, so how do we show polynomial equivalence? So this is shown up in several places now. So so let's just say we have a CNF sat, actually not CNF sat, what would be a better example? CNF sat and 3 sat. So recall that CNF sat is clauses of any length, and 3 sat is the ones of length, I don't know if I said at most 3 or exactly 3, but we might as well just assume at most 3. So these are not exactly the same problems, but they are equivalent in the sense that we had this notion of polytime reductions. So equivalence here in this setting just means that CNF sat poly reduces to 3 sat, and 3 sat poly reduces to CNF sat. So then they are equivalent in a certain sense up to a polynomial conversion between the two. So how do we actually show in this case how to do it? Well, this one we did in class, which is that idea of splitting a clause into 2 smaller clauses and then just repeating over and over. For this one right here, this says we got to transform an instance of 3 sat, so a formula with clauses of size at most 3, into a formula with clauses of any size. Well, what we can do is just provide the formula to the CNF sat one. We don't have to do anything different. So on input of formula phi, just produce phi. So in this case, this just means do nothing to the formula. Here, for the first one, we had to modify the formula, of course, to get it into the right format for 3-sat. But for C and F set, well, that just includes everything in 3-sat already, so we don't have to do anything special. So the first one we showed took polynomial time, and the second one takes no time at all, so therefore it runs in polynomial time. So that's a way to show equivalence, is, they're polynomially equivalent if we can do both directions of the reduction here. For the third question that was asked is how to create polytime verifiers and certificates. So how do we create polynomial time verifiers and certificates? So the vast majority of the time, this is really, really easy to do. And if you're spending a lot of time thinking about what the verifier is and what the certificate is, you're very likely thinking way too hard. So the way you should think about this, if you're stuck, is to say, well, what are the certificates and verifiers we've talked about so far? So for C and F sat, well, we're given a formula phi, some formula, and the certificate here would be an assignment to the variables. Because that's what the formula is, what the problem is really asking. Is there an assignment that satisfies the variables? And in this case, the certificate is some assignment. And the thing to notice here is that for a verifier, all that it has to do is just check this one assignment. It doesn't have to do anything else. So it's just to check if this assignment satisfies the formula phi. For, so what are the ones we did? So we did clique before, and we had the graph G and an integer K, and we wanted to figure out if there is a set of K vertices with every edge in between them, between every pair of vertices within those K. So, well, then what's the certificate here is just the K vertices. And the verifier just checks all pairs if an edge is there. So for all of these, including like independent set and the other ones that we did, so the certificate is basically the thing that you have to verify about the graph in the first place. Here we're given a graph and an integer K, and we want to figure out if there is a K clique within them. Well, the certificate would be a possible K clique, and then the verifier just checks it. So in the vast majority of the time, the certificate and the verifier are very straightforward. And if a NP complete question or whatever appears on the test, then on the final, then it will not be very difficult to figure out what the certificate is. It'll be very straightforward. So don't worry too much about this, because the verifier and the certificate will be straightforward if it will appear on the test. Okay, so the fourth question is, how do we show a language L is not in P? Oops. So how do we show a language is not in P? And remember that P is deterministic polytime. And so obviously undecidable languages are not in P because they can't be decided in polynomial time, let alone any time. So that's clearly a way to get this. But for finding a decidable language that is not in P, we don't have the technology yet. Or at least we didn't have enough time to talk about this. So don't worry about this. Okay, so but just note that there are techniques to show a decidable language that is not in P. So, but don't worry about it. So the fifth question is, let's see. So the question is, can you go over how to prove decidability when given L? So, how to prove decidability when given a language L and with input. So L is a set of machines of some form. So M is a machine in this case, but we want to prove a reduction from ATM, which is obviously the set of pairs MW such that M accepts W. Okay, so there's a clarification here. Like, how do we come up with the W part if it's not given in the problem? So for this one, you don't have to worry about it. This one either. So here, actually no, I got this wrong. Want to prove reduction to ATM. So we did a lot of what, I didn't talk about the exact term, but when we showed that ETM was undecidable, what we did was we supposed that it were decidable, and then we showed that ATM would be decidable in that case, but it's not. So that's a reduction from ATM to ETM. This is asking about the other direction. If we suppose that ATM is undecidable, then can we show some other language is... if we suppose that ATM is decidable, can we show some other language is decidable, but we don't know, but that language is undecidable, which proves that ATM is undecidable. And so we won't have to worry about that. And in fact, I don't even know of an example problem in which you do that sort of thing. So I wouldn't worry about it. Can you go over another reduction problem? Sure. So, so another reduction problem that doesn't use Rice's theorem. So no Rice's theorem. No Basmati. All right. And it actually says that we can't prove by Rice's theorem. So what one would that be? Okay. So here's one. So this one I think we have done before. Let me check. So I think we did this one in a quiz. Should be more prepared for this. Nope. Nope. Okay, yeah, so we didn't talk about this one. So this one is kind of familiar, which is instead for DFAs, we are doing it with Turing machines. So what is this language? It's pairs of Turing machines, which automatically tells us we can't use Rice's theorem for this. So M1, M2 are Turing machines, and the language of M1 is a strict subset of the second one. So if you haven't seen this symbol before without the little equal under it, this means strict subset. So what would you do here? Well, let's see. So what we can do is think about this. Well, what is a language that is on the extremities in terms of the language it accepts? So it could either be the empty set or sigma star. And there are multiple ways we can actually go about doing this. So we know that ETM is undecidable, so let's try to do that. Well, to figure out if a language is empty or not, well, let's suppose that the language of the second machine here in this pair has exactly one string in it. So if it has exactly one string and the language of M1 is a strict subset of this, well, since it's a strict subset, it must have smaller cardinality in terms of the language than this one does. Well, this one accepts one string, so therefore M1 accepts exactly 0 strings, which means that it's empty. But suppose that M1's language is not a strict subset of this. Well, then that implies that it's not empty. And then therefore, if we can solve this problem, we can solve ETM. So let's do this. So suppose that this whatever this language is decidable. Then we create a decider for ETM. Oops. TM. So always remember that ETM takes a single Turing machine. So on input M, where M is a Turing machine. So then what do? Well, let's create a Turing machine. I'm going to call it M1 because it'll only accept one string, with the language of M1 being, let's say, just the empty string. So this tells us that there is a string in this language, which means that it accepts this. So that implies that the language of M1 accepts exactly one string. And it's easy to make a Turing machine that does this, because we can make a DFA that does it. So then let's run the decider for SSUBTM on, so the input here has to be the 2 Turing machines that we have, M and M1. But note that the order really does matter here. So if I said M1, that's good, because this is asking if M's language is a strict subset of this language right here, which is what we want. But we can't use, for example, M1 first and M. So cannot do, I mean, we could do it, but it's just that it won't give us the result that we want. So here, this is saying that M's language is a strict superset of M1's language, which means that it accepts at least 2 strings, but that's not what we want to figure out for testing whether M's language is empty. So the order in this case does matter. For like EQ, DFA, or EQTM or whatever, the order doesn't actually matter because it's just whether they're equal or not. So then here all that we need to do is just output the same answer. Because why do we do that? Well, suppose that the decider says, yes, this language, M's, is a strict subset of this. Well, this implies that M's language is empty, but that's the answer that we wanted anyway for the emptiness question. If it's not a strict subset, then M's language is not empty, which means we're going to output no, which is what we want in the first case. Okay, so then this implies, of course, that since ETM is undecidable, SSUBTM is undecidable too. Cool. So yeah, so that's what you would do. Try to think for if you cannot use Rice's theorem, then you should be thinking about, well, in this case, well, is there some kind of extremity in which I could exploit some other undecidable problem? And another one you could do in this case is we could also do all TM, where the so what we can do is have we can test whether M2 accepts everything if M1 accepts everything but a single string. And then therefore, If M2 is a strict superset of M1's language, then that means M2 accepts everything. And if it isn't a strict superset, then that means M2's language isn't everything. So therefore, given a decider for SSUB, we can decide all TM, but it's easy to show via Rice's theorem or whatever that this is undecidable. Okay, and then the final question is, if we have to design a Turing machine, let's see, do we draw like the homework, one time, or an algorithm? And Christmas is coming in April and coming May, and for the reason, and why is that? Is because you will never have to draw a Turing machine. If you have to use a Turing machine or create one, you will always use an algorithm for it, because in all the other things I've already tested you on in one way or another, can you actually make a Turing machine? And the important thing is to understand that if you can make an algorithm for it, you can make a Turing machine for it because of the Church-Turing thesis. Okay, so those are the only questions I got for class tomorrow. Today on Wednesday. If you have additional questions, please send them to me by Thursday, preferably in the morning so I can make the video. And then I'll post the video on Friday if there are any questions. And if not, thank you for a great class. Please be in contact with everything that you do in the future. Thank you.